So we started this topic on second-order differential equations with ones of this type: second-order linear homogeneous with constant coefficients. And we started removing we removed the homogeneous aspect. So we then studied these kinds of things. Now I'd like to remove the constant coefficients aspect. So we'll keep homogeneous. We'll also remove that simultaneously on your homework. But for now, for this lecture, I'm going to remove constant coefficients and examine this situation. Except not totally in general. So this is what we're going to do for today and for Friday's lecture. So with these kinds of differential equations, they're still linear. So we still have linear, and that's the awesome part. So we still have, it's that you can write it kind of in this format, that it's some linear operator L applied to x equals 0, for homogeneous equals 0. So just because there's t's showing up here in your description of L, just because a and b are not constant coefficients, but possibly have t's in them, that doesn't make it not linear. It's still linear. So that's what's going to allow us to apply basically the same ideas for dealing with a homogeneous linear system and for using that homogeneous one to help us deal with the non-homogeneous. So to be fully general, let's suppose you also had non-homogeneous, and you have like f of t here. Then the differential equation still has this form where L is just more complicated. So it's still true that if you want to solve the homogeneous linear system and be able to handle any pair of initial conditions, you need two linearly independent solutions. That's still true, the so-called fundamental solutions. And it's still true that this step is an important step to helping you solve the non-homogeneous. So it's still true that if you can use some method to get at least one solution, like x sub particular, to the full non-homogeneous system. And it's still true that if you add them, then you get a general solution. To get general solution. What has changed in this setting where the A, B, and C can be time dependent, what has changed is that these steps are now different. To actually carry out the steps is different. The steps are the same, but the details of each step is different. So to get two linearly independent solutions, well, what we used to do, guess e to the lambda t, that's probably not going to work. That worked pretty much because the coefficients were constant. Remember, that allowed us to get a polynomial for lambda, which, after you cancel the common e to the lambda t term, you get kind of an equation for lambda that has no t's in it. If your equation has t's in it, then there's probably no way to choose lambda, to choose like one choice of lambda that makes the equation true for all t. So this kind of guess is not going to work. So you can still do this, but it's now hard. This is still the goal. Sorry, not you can do it. It's still the goal, but it's now hard. Maybe it's so hard that you cannot do it. And this is, I would say this is also hard, but it was hard to begin with, using the method of undetermined coefficients, trying to come up with a good guess. So this is still hard. So let's say this is now hard. It used to be not hard. It used to be that e to the lambda t always worked. This is still hard. Okay, so what I'm going to do actually is work on, for this lecture, I'll look at one very specific version of what a of t, b of t, and c of t could be. Just like this whole time we've been looking at one very specific version of what they could be, which is that they are constants. Now I'm going to look at another version, a non-constant, but very specific version, which is the following. I'm going to look at a of t being some constant multiple of t squared, and b of t being some constant multiple of t, and c of t being some constant multiple of 1, or just some constant. So I guess this one is not, still does not have variable coefficients. Only these two coefficients are non-constant. So this is the type of differential equation I'll look at, where you have a t squared instead of a times x prime prime plus bt times x instead of b plus c, or x prime, plus c x equals 0. So I'll start there, and then maybe we can also put not 0 here, and we can see. So you might complain and say, hey, this is like a really specific form of differential equation. How is this going to be useful? Well, I mean, so was what we were doing before, where we did have constants here. That was also a really specific form. So, I don't know, it might be useful. Okay, but to be honest, I have never found a use for it. So, mainly we're doing this because it's fun and interesting to see at least one case that we can handle where the coefficients here are non-constant. So, this section, I basically have no applications for you. I don't know of any. It's just going to be a mathematically interesting thing. These are called Cauchy-Euler differential equations. So Cauchy-Euler refers to specifically this form where you just choose A, B, and C. And you can make this have a more standard form if you just divide everything by A. So assuming A is not 0. If A were 0, then it's not even a second order differential equation, right? But just divide everything by A, like this. 0 divided by A is 0. Then you can get it to have this form where it's always 1 in front here. And then, might as well call this B, might as well call this C, right? So just call that B, call that C. So here's, still the most general form, just made so that this is a 1. All right, so today's lecture will be about these Cauchy-Euler differential equations. And Friday's lecture will be about sort of the more general picture, but we're definitely not going to have a way to just handle, non-constant coefficients fully in general and be able to write down the solution. They're just too hard. In fact, the main reason we're studying this one is that it's one of the few ones that we actually can do, which makes it fun.